This lecture we are going to perform static structural analysis on a cantilever beam. So coming to the problem description, what we can do is, see here there is a cantilever beam which is fixed at one end and is free at another end. The length of the cantilever beam is 100 mm and the cross section of the cantilever beam is the rectangular cross section with dimensions of 10 mm by 10 mm. Then a uniform load of 1 MPa has been applied on the top face of this particular cantilever beam, and see, this beam is made up of steel. So what we need to do is, we need to find out what are the different stresses that occur inside this particular cantilever beam, and also we are going to find out the value of the deflection that is going to occur inside this particular cantilever beam due to the applied load or pressure load of 1 MPa. To perform linear static structural analysis on a cantilever beam, what I am going to do is, I am going to go to the analysis system and going to select static structural and then drag it and drop it on the project schematic. And once I drag it and drop it on the project schematic, the first and foremost thing I need to do is, I need to define the engineering data or the material with which the cantilever beam is prepared. So according to the problem specification, what happens, the cantilever beam is made up of steel. By default, for every problem, structural steel is the material that is applied in the ANSYS Workbench. So right now what we need to do is, we can just continue with that default material, which is nothing but the structural steel material. So in this problem I need not give any engineering data, or I need not give any material properties for performing simulation. Then coming to geometry, so one thing is, I can create my own geometry in the design modeler, or otherwise I can import the geometry from the existing CAD file. So what I am going to do is, I am going to right click on the geometric cell and I am going to go to import geometry, then browse, and I am then going to select the beam STP. So this is the file that I have given you as a downloadable resource. You can just download it and then import it like this. And once you have imported the geometry, the creating geometry or importing the geometry step is also finished. Now what you need to do is, you need to open the model inside ANSYS Mechanical and then create the meshing, and then create the loads, creates the boundary conditions, and solve the problem and try to find out the values of deformation as well as the stresses. For that purpose, what I am going to do is, I am going to just double click on this model cell. So what happens if I double click on the model cell, the mechanical module inside ANSYS Workbench will be opened with the geometric data and the engineering or material data that we have supplied to the static structural system earlier using these two cells. So once the required geometry has been loaded into ANSYS Mechanical, the first and foremost thing you need to do is, you need to see whether the units are set to the units in which you want to view the results. Right now I want to perform simulation and want to view the results in mm, kg and other sorts of things. So I have selected metric, and it is fine. If you don't have the same units set up in your ANSYS Mechanical, you can just select it from the existing materials options, units option. Then the next thing you need to do is, you need to go to the geometry branch. You need to expand this geometry branch and select the solid body. And here, when you select the solid body, what happens, all the details regarding this solid body and what are the properties that I can edit are all shown in this details part of the ANSYS Mechanical window. So here, if I go to material and I go to assignment, see, by default the structural steel is the material that has been assigned to this particular object. As per the problem specification, I need structural steel to be applied to this cantilever beam, so I don't want to change the material assignment. See here, as I have told you earlier, the stiffness behavior is flexible. So if I change the stiffness behavior to rigid, what happens, even though if I apply the forces, I won't get any deformation, or the deformation of the body will be 0. For that purpose, I am going to leave the stiffness behavior to flexible. And then you can also check the dimensions of this particular object by going into the properties and here you can see what is the volume, what is the mass, and this particular mass is going to be calculated depending on the density of this particular structural steel. So if you have given a material without density, it will not be able to calculate the mass, or otherwise it will be showing ANSYS Mechanical will be showing some random value. Then you can also, for this particular object, you can also find out the centroid in x, y and z directions, and you can find out the moment of inertia and other sorts of things by accessing to the properties group. And if you go to the bounding box group, you can see the length in the x direction, length in the y direction, length in the z direction. You will be able to understand. See here, this is the global coordinate system. So with respect to these coordinates, these values will be created, or these values will be evaluated and shown to you. So now once we have set the material assignment to structural steel, then what I need to do is, the next thing I need to mesh this particular object. As this is a simple object, what I am going to do is I am just going to right click and on the mesh group, and I am going to just press generate mesh. So what happens is, as this is a very basic geometry, you can directly use whatever the options that are present inside ANSYS Mechanical to mesh this particular object. So once we have measured the object, the next step is to provide the loads and boundary conditions and then solve the problem. So we are going to do all these things in the next lecture. Once we have created the mesh, the next step is to give the boundary conditions. So in order to give the boundary conditions, what you need to do is, you need to select the static structural branch from this outline tree. This is known as the outline tree. So when you click here, there is a toolbar at this particular bottom of this toolbars. So this is known as a dynamic toolbar. So what happens, if I just change the selection of the group, this particular toolbox will change according to the type of selection you made from the outline tree. So for example, if I am going to select static structural, it is going to change into environment toolbar. If I just select the solution group, it is going to be turning into solution toolbar. This particular toolbar is very much useful in order to apply different types of boundary conditions, as well as different types of boundary conditions, supports and other sorts of things. Then coming to static structural, what I am going to do is, I am going to go to the environment toolbox, and as specified in the problem, we need to fix this end and we need to apply a pressure of 1 MPa on this top surface. So for that purpose, what I am going to do is, I am going to select this static structural, and I am going to go to the environment toolbox. And don't worry, there are different types of toolboxes here, and you don't worry about all these toolboxes. As we are going to perform a number of simulations in this particular course, you will be able to learn different options from these toolboxes which are necessary. So for now, we are going to go to the environmental toolbox, and then we are going to select the support, and in the support we need to fix this end. So I am going to select the fixed support from here. So once I select the fixed support from here, I can just rotate this particular object. So in order to rotate this object, you just need to press down the scroll wheel, and then you can just rotate by dragging it. And once I am satisfied with the rotation, I can just select this particular face, and I am going to press apply. So see here, there is one toolbar known as the selection toolbar, which is very useful. So for example, if you want to select only faces from the object, you will be selecting this particular option, which is nothing but the face select option. So if you want to say, for example, if I select this particular option and I want to just select this vertex, I will not be able to select the vertex, or I will not be able to select the whole body, or I will not be able to select a single line. So for that purpose, if you want to select lines or edges, you need to go to the edge selection tool, which is present here, and you need to press this button or press that particular option on that particular option, and then see. Now what you are going to do is, you will be able to only select edges or lines. You will not be able to select the bodies, you will not be able to select the vertices, you will not be able to select any faces. Likewise, if you want to select the total body, you can go to the body selection. So depending on the type of selection you are doing, you need to select from this, you need to select options from this toolbar. So here I need to apply fixed support to a face. So what I am going to do, I am going to select the face selection. Then we have clearly fixed this particular beam. So here once you have selected the boundary condition, it is going to be represented in a color. See here. So what happens here, the face is being represented blue in color, and on this graphics window you are able to see that blue color indicates that there is a fixed support on this particular face, and you can get information here, fixed support. Then now what I need to do is I need to apply pressure. So in order to apply pressure, you need to go to the environmental toolbar, and then you go to loads. In the loads drop down menu, you are going to have access to the pressure. In not only pressure, you will be having access to number of options or number of types of loads that you can apply in ANSYS mechanical. So I am going to select pressure. So once I select the pressure, now what I need to do is I need to select this top face. So I have selected this top face. So once I selected this top face, I need to click apply here. So whenever you select for applying a boundary condition, or say for applying a load, you just need to select the face or the entity on which you are going to apply the boundary conditions or supports. And once you have selected that particular entity, that entity may be either point or say line or edge or a total body also. Once you have selected that particular entity, you need to come into the details section and you need to apply, press on apply. Otherwise what happens is you will not be able to apply that particular support to that particular entity. So this particular options can be accessed from details part, in details part from the scope group, and you can have this geometry. So the default scoping method is geometry selection, and we are going to see in the further lectures how we can change this scoping method and what are the different scoping methods available, and where we are going to use different scoping methods rather than selecting a geometry like this. Once you have applied this particular geometry, then you need to define the magnitude. So here the pressure is a vector where it is having a direction as well as it is having a magnitude. So the magnitude here is 1 MPa. So I just have entered 1 MPa. If you don't see the units defined as MPa, one thing is you can go to the units here and you can change the units, or otherwise you can convert the 1 MPa to whatever the units that are being referenced here. So for example, if force unit is being shown as Pascal, you need to change 1 MPa into Pascals, that is you need to multiply 1 into 10 to the power of 6 in order to convert MPa to Pascals. Then see, once I am satisfied with the direction, see this direction is towards the downward direction. So this is the direction in which I want to apply my force, so I don't want to change the direction. So here you can define the direction in 3 different methods. One method is the components method, another one is the vector method, and the other one is the normal method. So for example, if the defined by method is to normal method, what happens? If I select any face, the force will be applied normal to that particular face or perpendicular to that particular face. But if I go and select vector, what happens is I need to define a magnitude here, and once I define the magnitude, I should be manually applying I should be manually selecting the direction. So if I just click here and then I can select any of the lines, see any of the straight line in order to define the direction, and you can press apply here. So if the option is normal to, it will automatically, whatever the face we are going to select, it is going to place the force normal to that particular face. But if it is in vector, we need to define the direction manually and we need to define the magnitude. It is 1 MPa. Okay, so 1 MPa. Now the direction is good. But say if I don't like the direction and I want to apply the force in the top direction, what I can do is I can just click on this direction option once again in the details view, and then I am going to just press on this arrows. See here. Likewise, I can just change the direction. Then I can give -1 also. So in order to change the direction of the pressure, and then I can also define it through components. So in components means what happens, these components are based on the global coordinate system. This is the x component, y component and the z component, and in whatever direction I want I can give the pressure. So I want the pressure to be in applied in the y direction. So what happens, I am going to define 1 MPa in the y component. Now what happens, see, the direction is towards the upper side, but we want to apply the pressure to the lower side of this particular object. So what you need to do is you just need to type in minus 1 MPa so that the angle, also direction of the applied pressure will be changing. So this is how we can apply boundary conditions as well as loads to the cantilever beam. So the next step is to solve the problem and find out the stresses as well as the deflection inside the beam, which we are going to see in the next lecture. Finished applying all the loads and boundary conditions. Now what we need to do is we need to solve this particular problem. So I am going to click on here to solve this particular problem, on the solve button to solve the particular problem. What happens, it is going to create the global stiffness matrix, global displacement matrix, global force matrix, depend on the boundary conditions, geometry, material properties and everything, and it is going to solve all the equations, and then it is going to find out the deflections at each node, and once it finds out the deflections at each node, it is going to interpolate that particular values using something known as the shape functions, and then it is going to represent the deformation, it is going to represent the stress, it is going to represent the strain throughout the total body. Now see, once I have solved this particular problem, now what I am going to do is I am going to select the solution group from the outline. So once I select the solution group from the outline, I can ask for different sorts of results. So for this particular problem, I am going to ask for a total deformation, and I am also going to ask for a directional deformation. And then the next step is we need to find out the equivalent stresses or von Mises stresses. So for that purpose, I am going to go to the stresses group. In the stresses group, I am going to select the equivalent von Mises stresses. And remember, depending on the type of analysis you are doing, because ANSYS mechanical can support lots of types of analysis, like say model analysis, advanced dynamic analysis, transient analysis, fatigue analysis, lots of other nonlinear analysis. So depending on the type of analysis, whatever the results you are going to find out will be varying. So here you are only performing linear static structural analysis, so you will be getting only some type of results. But if you are going to change the type of analysis to dynamic analysis, there the number of solution options that are available will be changing. So once I have done all these things, I am going to just right click on the solution group once again, say evaluate all results. So what happens is, evaluating all results means whatever the results that have been created and that can be only understood by the computer will be converted into the results which we have requested here. Okay, now if I click on this total deformation in the outline tree, see, I am able to have or I am able to see the value of deflection inside this particular cantilever beam, which is displayed on the graphics window. See here in the graphics window, you can see the result we are seeing or we are watching is the total deflection, and the units it is being represented is in mm. And see here, I have got a maximum deflection of 0.75063, and this particular maximum deflection is at the free end. As we already know, at the fixed end the deflection will be 0, and at the free end the deflection will be the maximum. So this is the total deformation. But coming to directional deformation, so instead of selecting the total deformation, you can even see what is the deformation in each direction. It may be x direction, it may be y direction, or it may be z direction. So in this particular problem, we have applied the pressure in the downwards or negative y direction. See here, negative y direction. So what I need to do is I need to change the axis of calculation from x-axis to y-axis. So what happens, see here, by default in the definitions tab you are going to have the orientation set to x-axis. So whenever you put up directional deformation, the orientation by default will be x-axis. But here in this problem, I want to see the deflection in the y-axis direction. So what I am going to do is I am going to change this orientation from x-axis to y-axis, x-axis to y-axis. Once I select this x-axis to y-axis orientation, I need to once again update this particular result. For that, what I'm going to do is I'm going to right click on that particular result and I'm going to request for evaluate all results once again. So once I have done this, see here, we have got the deflection, and this deflection is in the y direction. This deflection is in y direction. So what happens if we take this particular end, it is 0. So it is a fixed end. At the free end, we are going to get a maximum deflection of 0.748 mm. So it is represented in a negative value because whatever the deflection we have calculated, it is in the negative y direction. That is why it is representing that deflection as negative. And coming to the contours, so in the total deflection, see, the highest deflection was represented by red, but here what happens is, here also the highest amount of deflection according to the software is 0, because if we take negatives, 0 is the highest number. So that is why it is representing the highest value here and the lowest value in blue color here. So as an CA engineer, you should not go away with seeing different colors, and you should not be telling based on the colors, you should not be saying whether the component has failed or not. You should be able to understand these particular results, and you should be able to interpret these particular results. So coming to the final one, which is nothing but the equivalent stresses, you can see the maximum amount of stress has occurred at this particular constrained end. So what happens is, when we apply the force, in addition to the stresses that are induced inside the body, there will be some reaction forces that are caused due to fixing of this particular end, and these two add up and we get the maximum amount of stress here at the constrained end inside a cantilever beam. So this is how you can request for results, and you can perform linear static analysis on maybe a cantilever beam, or it may be some other simply supported beam. If you are going to calculate simply supported beam, what we are going to do is, instead of fixing this end, we are going to select this edge and that particular edge, and we are going to fix two different displacements only. We are not going to fix any third displacement, and we are going to apply the pressure here on the top, and we are going to find out the results. Now if we want to understand even more, if you want to understand these results even more, you can just press on this animation button. So there is a graphics section here in the ANSYS mechanical window where you can just press on this play button, so that it is going to play, and you will be able to see an animation of the stresses being developed inside this particular cantilever beam due to the applied pressure. So in the next section, or the next problem which we are going to deal is, we are going to take a pneumatic cylinder cover, and then we are going to apply pressure on it, and we are going to perform a linear static structural analysis on a pneumatic pressure cylinder cover. Thank you. In this problem, we are going to perform analysis on pneumatic cylinder cover. So the cylinder is designed to hold a pressure up to 0.5 MPa and is generally made from aluminum alloy. But for this particular problem, we are going to manufacture this or produce this particular part with engineering plastic, which has an Young's modulus of 22 GPa and a Poisson's ratio of 0.3. So what is the most concerned thing in this particular problem is, we need to find out the deformation of this inner circle, and see, as per the specs, the circular deformation should be less than 10 micrometers, and if it exceeds some 10 micrometers, what happens, the airtight seal will not be there, and the gas will be lost, and the pressure will be lost from this pneumatic cylinder cover. See here, there is an example of a pneumatic cylinder cover, and this is the part with for which we are going to perform the analysis. In order to perform the analysis on a pneumatic cylinder cover, I have opened ANSYS Workbench, and once I have opened ANSYS Workbench, I am going to go to the static structural inside ANSYS systems and drag it and drop it on the project schematic. And once I drop it on the project schematic, now what I am going to do is, I am going to specify the engineering material with which I am going to produce the part. So I am going to just double click on the engineering data cell in order to open the engineering data manager. And once I open the engineering data manager, as I've already told you, by default structural steel is the material that is defined. We need to change this material. So in order to add new material, you need to click here, and once you click here, you need to enter what is the name of the material you want to enter. So our material is, say, engineering plastic. So I have typed it in the name and I just press enter. Now once I have just press enter, I need to define the Young's modulus as well as the Poisson's ratio. See here, the engineering plastic is an isotropic material. So it is going to have only one value of Young's modulus and one value of Poisson's ratio. So for that purpose, I am going to go, in order to define the Young's modulus, I am going to go to the toolbox and I am going to go to the linear elastic tab. In the linear elastic tab or group, I am going to select the isotropic elasticity and then drag it and drop it on the engineering plastic material. And once I have just dragged it on the engineering plastic material, see here in the engineering plastics data, we need to enter Young's modulus and Poisson's ratio in this yellow color cells. So here, in order to define Young's modulus, the unit is being displayed as pascals. One thing is, we can convert this 22 GPa into pascals by multiplying 22 into 10 to the power of 9, or otherwise what we can do is we can just come down here and change the units from Pascal to MPa, and then we can convert 22 GPa into MPa by multiplying it into 10 to the power of 3. But for now, what I am going to do is I am going to revert back to pascals again, and I am going to enter 2.2 E10. So that means what I am going to do is I am multiplying 22 into 10 to the power of 9, or 2.2 into 10 to the power of 10. Then coming to the Poisson's ratio, we need to be defining the Poisson's ratio, which was given as 0.3. These two are the basic properties that are required in order to perform a simple static structural analysis. So once you are satisfied with this particular material properties, then you can just close this particular tab. And once you close the particular tab, then the next thing is you need to import the geometry. For importing the geometry, I am going to right click on the geometric cell, say import geometry, say browse, and then I am going to select the pneumatic cylinder cover and I am going to open it. And now the geometry has been successfully imported into the workbench. Now what I am going to do is I am going to double click on the model cell. Once I double click on the model cell, I will get access to the ANSYS mechanical module, wherein I will be doing the meshing and I will be doing all other operations. So once the geometry is loaded inside ANSYS mechanical, now what I am going to do is, first thing is I need to check my units. So I am going to go to the units and check whether my preferred units are selected or not. Right now my preferred units are selected here. I don't have a need to change the units here, so I'm going to go back. Then the next thing is you need to go to the geometry cell, expand the geometry cell or geometry group, and you need to click on the solid body which is available there. And in the definition, see, as I've told you, by default structural steel will be assigned to this particular body, but what I need to do is I need to change this structural steel to engineering plastic. For that purpose, what I am going to do is I am going to just click on the edge of this right edge of this particular assignment cell, and then I am going to get a list of materials that are available for present analysis. So I have added in addition to structural steel, I have added engineering plastic. If I add some 10 materials, those 10 materials will be shown here in this particular list, but I have added only engineering plastic, so it is only showing one option. So I am going to select this engineering plastic. Now see, the assignment of the material of this body has been changed to engineering plastic. Now I am going to go to mesh. In the before example, where there was a very simple body which is a cantilever beam, rectangular cantilever beam, we had used the options, default options to generate the mesh. Right now also what we are going to do is we are going to just mesh this particular body with the default mesh settings, and we will see whether the quality is right or not, and then we are going to again remesh it using some settings. So I am going to just right click on the mesh and I am going to say generate mesh. So here the meshing is done, but you see at this circular faces, if you want more accurate results, you can refine this particular say mesh. So in order to refine this mesh, one thing is we can change the settings of the mesh. So in order to change some settings of mesh, you can just select this mesh settings, and in the relevance, in the physics preference I will leave it to mechanical because I am going to do perform analysis in mechanical itself. In the relevance, what I am going to do is I am going to just refine it by just entering 100 and just pressing enter. And once I have done this, see what we are going to do is we come to the statistics here. So I am going to expand the statistics. So with the default settings we have used and we have measured this particular object, we got some 11,104 nodes as well as 5,861 elements. But now what we have done is we have changed the relevance settings from 0 to 100. Now what we are going to do is we are again going to regenerate the mesh. So in order to do that, you just right click on the mesh group and you say generate mesh, or you can also ask to update the mesh. So right now I am going to just generate the mesh once again. So see now if you are able to see, after increasing the relevance, see here the number of nodes has increased from say 11,000, it has increased to 26,000, and the elements somewhere like 4,000 or so have increased to 14,000 or so. So what happens is, if you are going to refine the mesh, the number of nodes as well as the elements are going to increase, and the number of equations to be solved are going to increase, and the more time will be taken for the analysis to complete. Once I have finished the meshing, the next step is to give out the boundary conditions as well as the loads and then solve the problem, which we are going to do in the next lecture. This lecture we are going to define the boundary conditions as well as the loading conditions to this particular problem. So as per the specification of the problem, we are going to have to apply a pressure of 0.5 MPa on the internal circular surfaces of this particular say pneumatic cover. Then we need to fix this particular holes. So what happens in the real world, what happens, it is going to be fixed to the cylinder using the bolts. So in order to simulate that, we are going to use the frictionless support instead of fixed support. So what I am going to do is I am going to go to the static cell group. In the static structural group, I am going to select the supports. In the supports, I am going to select frictionless support. So once I select the frictionless support, you need to select all the internal faces of this holes. So there will be a total of 12 faces you need to select. So in order to select multiple faces, you need to press Ctrl and then only you need to select multiple entities. So I am going to select all these holes. See here, all the faces inside the holes. So there will be a total of 12 faces, and you need to get that quantity right in order to get the results right. Then I can just rotate it like this. So I can just select the inner surfaces, and now once I am satisfied that I have selected all the surfaces, I can just press apply here in the scoping option in the details and say apply. See here the number of faces for which we have applied the boundary condition or the loading condition will be shown here. So as I require 12 faces, I was able to get 12 faces. Now the next thing is I need to apply pressure for this internal faces. So what happens is there will be a total of 39 faces which I need to select to apply a pressure of 0.5 MPa. Then I will just click on the static structural and then go to the loads, and in the loads I am going to select the pressure and I am going to select the internal faces. Just like previously, as I have selected multiple faces by pressing Ctrl, you can just select by pressing Ctrl, or you can also by pressing Ctrl you can just drag over whatever the faces you require to select, then it will be automatically selected. That is one other option. So once you have done selecting all the faces, then you can apply the pressure. Now I have some faces remaining and I need to select it manually without dragging, because I was not able to drag it onto that particular faces for selection. So I think yeah, there is one face left here, and I think there is one more face left here, and one face left here, and there is a face left here. So I think I have oh yeah, there is a face select. I think I have selected every internal face. Now what I am going to do is I am going to just apply. See, I have got a count of only 34 faces, but I do know that I need to have a 39 faces. So I will just search for the faces which I haven't selected. See here, I haven't selected these 4 5 faces. So what I'm going to do is I'm going to just press Control and I'm going to just click on this geometry scope once again, and then I'm going to select these additional faces. If you don't press Control and select the geometry option, what happens, the previously selected faces will be overwrite. I'm going to select this face as well as this face. I think I have selected 4 faces out of 5. I'm going to just rotate it once again and I will find out. I think this is the face I need to select. Yes, I think I have selected every face and press apply. Oh no, I haven't selected this face again. So what I'm going to do is I need to select another 2 more faces. So okay, so I'm going to select this face, and what is the next face I need to select? I was not able to find out. Okay, this is the face I need to select. So I'm going to just press Control once again. I'm going to select this geometry, and then I'm going to just select this face as well as this face. Now I press apply. Oh, right now I got only 37 faces. Oh, I need to select this face, and again, what is the face I need to select? Extra face. I need to select this face as well. So once again I press Control and the geometry, and I'm going to select this face. Then I'm going to select this face as well, and just press apply. Now the count is 39 faces. So once I've taken I've selected all the 39 faces. Now what I'm going to do is I'm going to give a magnitude of 0.5 MPa, and the direction of this application is normal to the surfaces, so it is fine. So we have applied the boundary conditions as well as the loading conditions here. So in the next lecture we are going to solve the problem, and then we are going to find out different results. Thank you. Once I have applied the required boundary conditions as well as the loading conditions, what I am going to do is I am going to click on solve to solve this particular problem. I think it will take a little bit of time, not much time, because there are a lot of curves and number of nodes, and the elements are more in comparison to the previous problem that we have solved. And then once you have finished this one, the first and foremost solution we are going to get is we just right click on this particular solution group, and we can also say insert. Instead of going to this solution toolbar, we can just right click on the group, solution group, and say insert, and I can also get access to this different tools from here also. So I'm going to put up deformation, that is the total deformation I'm going to find out, and then I'm going to say insert. I'm going to find out the equivalent stresses, total stresses, and also I'm going to find out the maximum principal stresses, and I'm going to just right click, say evaluate all results, to find out what is the value of total deformation. So the total deformation value is somewhere around 0.008 mm. So it occurred at this particular point, at this particular point, or at the middle of this particular say this cap. Then I'm going to go to the equivalent stresses, and the maximum equivalent stress was 11.2 MPa, and then the maximum principal stress was around 10.673 MPa. See here, when you are going to select any option, you can see the information regarding that option, what are the units in which result is being displayed, and what is the type of result that is being displayed. You can watch from here. Then once you are satisfied with this, now what I want to do is I want to find out the say radial stresses, axial stresses, as well as this circumferential stresses inside this particular round cylinder. So this particular say technique or this particular process can be used when you are trying to solve a problem, a pressure vessel problem, and then you want to find out the axial, radial, as well as the hoop stresses. So for that purpose, what I need to do is I need to create another coordinate system. By default, the global coordinate system is a Cartesian coordinate system. But for finding out the circumferential stresses, we need to create a new coordinate system, which is a cylindrical coordinate system. So in order to create a coordinate system, what you need to do is you need to go to the coordinate systems group, and then right click on the coordinate system group, say insert, and create a coordinate system. So once you click on this, there are number of options that are related to this coordinate system that are displayed in the details of coordinate system part. So here in the type we need to change it from the Cartesian coordinate system to the cylindrical coordinate system. So once we change it to cylindrical coordinate system, now what we need to do is we need to select the geometry for which we are going to apply this particular, say, local coordinate system. So I'm going to select this one and I'm going to select this inner face, then I'm going to say apply, or otherwise you can select the total body. It doesn't have any change. So once you have done this thing, you can just leave it. So we have created a coordinate system, new coordinate system, and it is a local coordinate system. It is not a global coordinate system, it is a local coordinate system that we have created. So right now, in order to say distinguish, I can just rename it by pressing F2, and I will rename it as a cylinder or cylindrical coordinate system, or whatever it is, just to identify. So once you have done this, see, coming back to the stresses, we have normal stresses. So we use the normal stresses concept, and by defining the direction of normal stress, we are going to get the stresses in the radial direction, axial direction, as well as the circumferential direction. So what happens, I am going to right click on the solution, go to insert, go to stresses. Instead of selecting equivalent stresses, I am going to select the normal stresses. So once I select the normal stress, here see, in the definition there is something known as the orientation and coordinate system definition. So in order to get the radial stresses, you can either use the global coordinate system, or you can also use the newly created cylindrical coordinate system. So I am going to change this coordinate system to cylindrical coordinate system, and now see, if I come to the cylindrical coordinate system, if you observe that the x direction is in the radial direction of this particular circle, and then z is in the direction of axial direction, and this particular y is in the circumferential direction to this particular cylinder. So by specifying or by finding out the normal stresses in 3 different directions, you will be able to have the value of say axial stresses, radial stresses, as well as this particular circumferential stresses. So now what I am going to do is I am going to leave this orientation to x-axis. So what I am going to get here is the radial stresses. So once I have done with this, I am going to rename this so that I can easily identify. So I am going to rename it as a radial stress. So now the next thing is, you can just go back to solution once again. You can just say insert and go to the stresses, and you can once again select the normal stresses, and then in the normal stresses you can rename this normal stresses as the axial stresses, and then you can change the direction from x-axis to the y-axis, and change the coordinate system from global coordinate system to the cylindrical coordinate system. So what happens, see, if you come and watch this particular cylindrical coordinate system, this particular z-axis is aligning with the axis of this particular cylindrical face which we have selected. So we are going to get the values of axial stresses here. Then another thing you can do is, you can just right click on any of this solution option, you can just copy it, and then you can come back to the solutions tab. You can right click and say paste here, so that you can paste this particular options which you have copied earlier. So I am going to rename it as a circumferential stresses, okay. Then here instead of the orientation be, sorry, here I think yeah, in the axial stresses we have set the orientation to y-axis instead of z-axis. I have right now found it when I have just selected this circumferential stresses. So I am going to change it to z-axis instead of y-axis, it is to z-axis. Then coming to the circumferential stresses, the orientation is y-axis. See, according to the local coordinate system, the orientation to find out circumferential stresses should be in y direction. So it is in y direction, so we are going to leave it there itself. So once we have done all these things, we can just right click and say evaluate all results. Now you can see, if I select on this radial stresses, you are going to get a value of the radial stresses that have been developed. Then coming to this axial stresses, you are going to get the value of axial stresses, and then you are going to get the circumferential stresses. So we have found out the method of how we can find the radial, axial as well as circumferential stresses in any cylindrical object. Okay. Then according to the problem, we need to find out the deflection, directional deflection of that circular surface, and find out whether it is going to exceed the 10 micrometers mark or not. Already by using the total deformation, we have got a specific idea that it hasn't crossed the 10 meters mark, but 10 micrometers mark, but we are going to do that also in the next lecture. What we are going to do is we are going to find out the directional deformation, and we are going to see how the cylindricity of this inner circular face is going to be disturbed, and as per the problem we should be having a deflection which is less than the 10 micrometers mark. So for that purpose, what I am going to do is I am going to go to the solutions group, and I am going to right click on the solutions group, say insert, and go to the deformation, and instead of selecting total deformation, I am going to select the directional deformation. And once I select the directional deformation, I am going to select this particular inner face, and I am going to scope it. So once I have scoped the result to this particular surface, what I am going to do is I need to give the direction. So if you compare, see, we want the deflection in the radial direction, and according to the global coordinate system, you can either define x, or you can also either define y for this particular problem, because you see x axis is in the radial direction as well as y axis is also in the radial direction to the surface which we have selected. And for now we are going to keep the orientation to this x axis itself, or otherwise we can also change the global coordinate system to say cylindrical coordinate system. Even in the cylindrical coordinate system, the orientation of this x axis is in the radial direction to this cylinder, so we can just leave the orientation to x axis, and then we are going to right click and say evaluate results. And once we evaluate the results, here see the maximum deflection that has occurred is 0.00763 mm. That means the deflection is somewhere around 7 micrometers, which is less than the specified value of 10 micrometers, so that we can specify this particular design can hold good for a cylinder carrying up to 0.5 MPa pressure, and using the material ABS plastic also we can produce this particular product or this particular component. So in the next lecture we are going to see how we can perform analysis on a circular LED stand. Thank you. So here in this particular problem, we are having a circular stand for an LED TV like this. Somewhere like you see, this is a curved LED TV, and we are going to have a stand. So this particular monitor will be attached to this stand through a bearing which is rotatable. So we have taken this LED circular stand. Then it is made up of ABS plastic whose Young's modulus is 2.62 GPa and a Poisson's ratio of 0.34. And from the tensile tests, it was known that the ABS plastic will start to develop cracks at 37 MPa of stress, and then it is going to fully fail at a stress of 54 MPa. So the weight of this particular LED screen which it is going to support is somewhere around 42 newtons. So what we need to do is we need to find out the stresses and deformations inside this particular circular stand and determine whether our design is going to withstand this load or not in terms of both the stresses as well as the deformation. LED stand problem, we have opened ANSYS Workbench once again, and I am going to drag the static structural analysis system onto the project schematic, and once I have dragged it to the project schematic, I am going to define the engineering data or material. So I am going to double click on the engineering data, and here I am going to add a new material which is nothing but ABS plastic. So once I have added this ABS plastic, the first and foremost thing is I need to define the Young's modulus and Poisson's ratio. In order to define these two things, I need to go to the toolbox, I need to go to the linear elasticity, and I am going to select this isotropic elasticity, and I am going to just drag and drop it on this ABS plastic. And once I have done this, I am going to specify the Young's modulus. here the units are pascals, but the units in which the problem has been specified is in GPA. I am going to convert this GPA into pascals by just multiplying 2.62 into 10 to the power of 9. So I am going to just type in 2.62 E9, and the Poisson's ratio is 0.34. So as I have told you in the introduction to static structural analysis, in the properties, what are all the properties that are needed to be defined for this static analysis? You need to define a property known as the failure property in order to assess the safety factor. For that purpose, what I am going to do is I am going to go to this strength group. In the strength group, I am going to take tensile yield strength, and I am going to place it on this particular ABS plastic, because according to the problem we have seen that this ABS plastic was tested using tensile testing, and it was said that it was developing cracks at 37 MPa and it will fully fail at 54 MPa. So for better design, what we are going to consider is we are going to consider 37 MPa as our ultimate failure load. So that is the value which we are going to give here. So I am going to change this particular units from Pascal to MPa, and I am going to just enter 37 MPa, 37 value, and I am going to press enter. In the previous two examples, we haven't specified this yield limits or strength limits, because we haven't performed any analysis like a safety factor of safety analysis on those problems. We just wanted to find out the deflection and the stresses, but here we just want to perform factor of safety analysis, and we also have to fully define whether our design is going to fail due to stresses or deformation. So once I have given this particular value, what I am going to do is I am just going to close this particular engineering data. And now I am going to just right click on the geometry cell. I am going to just import the geometry. I am going to browse, and I am going to select the LED TV support geometry, and I am going to press open, and this imports the geometry into this ANSYS Workbench. Now what I am going to do is I am going to double click on the model cell, and I am going to get access to this ANSYS mechanical. See, once I get access to this particular model, the first and foremost thing is I will check for the units, whether the units specified are the units which I want, or otherwise I can change it from here. And then I am going to go to the geometry, expand this geometry branch, and I am going to select this particular geometry. And see, as I've told you before, only the assignment by default will be structural steel. You need to change it to ABS plastics, and once you have changed it to ABS plastic, now what you need to do is you need to mesh this particular object. So I'm going to leave the meshing options to default, and I'm just going to right click and say generate mesh. So I have generated the mesh. So for now what I'm going to do is I'm going to leave this mesh like this, and I'm going to solve the problem. Then as we have generated the mesh, the next thing we need to do is we need to apply the loads as well as boundary conditions to solve this particular problem. That is the thing we are going to do in the next lecture. We are going to apply the boundary conditions and the loading conditions. So what I'm going to do is I'm going to select the static structural, go to insert instead of going to the environment toolbar, and what I'm going to do is I'm going to select I need to fix this bottom part of this see, I need to fix the bottom part of this particular body. So instead of just selecting this fixed support, I can just select the displacement, and in the displacement I will select this face, and I'm going to apply. And then see here, instead of keeping every component free, if I just fix every component, x direction component, y direction component, as well as z direction component, I am going to simulate the same boundary conditions which is equivalent to the fixed boundary condition. So this is how, using the displacement option, you can create a number of variety of supports without even having access to latest options. So once you are done with this, you need to go right click on the static structural, say insert, you need to select the bearing load, and once you select the bearing load, the first and foremost thing is you need to select a circular face where the bearing is going to stay, and this is the circular face on which the bearing is going to stay or attach it. So I'm going to select that circular face and going to apply, and once I apply, see here, I need to give the magnitude. So the magnitude is nothing but the force that is applied through that bearing. So what is the force that is applied through the bearing? It is nothing but the weight of the LED TV. So it is around 42 newtons. So I am going to enter 42 newtons. See here, this particular value has been defined through vector, and see the direction is showing like this. But when you take this LED TV, what happens? The weight should be, or the force should be acting in the vertically downward direction. So what you can do is you can just click here on the direction, and instead of selecting that particular line, you can select any straight line from here, straight edge from here, and you can see this particular direction, and you can just switch the direction to opposite and press apply. This is one thing, or otherwise you can change it from vector to components, and you can define this 42 newtons load in the negative y direction, So this is how we are going to apply the boundary conditions for this loads and boundary conditions for this problem. In the next video, we are going to solve this particular problem, and we are going to see different results. Conditions as well as this loads, we need to solve this problem. In order to solve the problem, I can click here to solve, or otherwise I can just right click on the solution group and say solve, or I can also just press F5. If I select this solution group, I can just click on F5 to solve. So once the problem has solved, now what I'm going to do is I'm going to go to the solution, say insert, and in the insert I'm going to take the deformation, and I'm going to take the directional deformation, because my load is totally acting in the y direction, negative y direction. So instead of finding out the total deformation, I can just go to the directional deformation and change the orientation to y from x-axis, and I'm going to find the deformation. Say I'm going to evaluate the result. So see, the maximum deformation is somewhere around 0.29 mm. As I've told you previously, it is shown in minus because it is in the negative direction. So what happens? 0.29 mm on a total scale of a total body, it is not a much deformation which we can consider. So I think with respect to deformation, this particular product hasn't failed, because if there is excessive deformation inside the body, then we can say with respect to deformation this particular part has failed. But here there is only a minimum amount which is like 0.29 mm. So we can say confidently that this particular object hasn't failed due to deflection. Now the next option we need to see is, we need to see whether this is going to fail due to the stresses that are going to be induced into that particular body. So for that purpose, what I'm going to do is I'm going to go to the solution once again. I'm going to insert, I'm going to stresses, and I'm going to select the equivalent von Mises stresses. And once I selected this equivalent von Mises stresses, I'm going to just evaluate this results. So once I evaluated the results, so here the maximum equivalent stress is 3 MPa. But according to the problem specification, what we have seen, this particular body is going to develop cracks if the stress is equivalent to 37 MPa or more. So from this we can say that the equivalent stress is very much lower in comparison to 37 MPa. So we can definitely say this particular object hasn't failed due to the load, due to the stresses that has been developed inside the body. But we are not going to stop here. What we are going to do is I'm going to just go to the solution, just say insert, and in the stresses I'm going to take maximum principal stresses, and I'm going to say evaluate the results. Once I have evaluated the results from the maximum principal stresses, also the maximum stress is somewhere around 3.0953 MPa. So from this two results we can say effectively say that this particular body is not going to either fail in deformation or also the stresses produced inside the body. Now what we are going to do is I'm going to just right click on the solution once again, go to insert, and I'm going to go to the tool known as a stress tool. So I'm going to go to the stress tool. In the stress tool also I'm going to go to the maximum equivalent stress, or otherwise what I'm going to do is I'm going to go to the solution toolbar. I'm going to get a stress tool here. So from the stress tool, what I can do is I can calculate the factor of safety for this total body. So from the stress tool you can calculate the factor of safety. You can just right click and say evaluate results, and now you see the factor of safety is somewhere around 12 to 15, which is very high in comparison with the particular product. It is very high. So one thing you can do is you can just change the material to a lower failure, let us say a material which has lower yield strength and lower cost, rather than getting to this ABS plastic, or otherwise you can just change the thickness of this particular object. So then once we have finished this test tool, what I'm going to do is I'm going to go to the solution once again, and I'm going to insert, say in stresses, I'm going to find out the error. So I'm going to find out the structural error. So I'm going to just evaluate this result. So we are going to see what is the benefit of structural error in the next lecture. Or we have calculated the structural error, and you don't need any of these values. So don't worry about what is structural error and how it is calculated from convergence and other sorts of things. You just need simple fact that in whatever areas there is high structural error, you can just refine your mesh at that particular area. So for example, for this problem, what happens near this edge, we have more amount of structural error. So what I'm going to do is I'm going to go to the mesh. Now I'm going to put up some local conditions or local refinement controls in order to modify my mesh. So I'm going to right click, say insert, and I'm going to say sizing. So once I select the sizing, I'm going to select, see here I'm only able to select the faces, but right now what I want is I want to select only edges. So for that I'm going to change my selection tool to edge selection, and I'm going to select this edges. See here, by pressing Ctrl I'm going to select multiple edges. See, I'm selecting this multiple edges. So what happens is, instead of refining the total body, if you refine it locally, what happens, the number of equations to be solved, or the number of nodes or elements that are formed, will be lower, and we can have a much efficient solving process or much efficient solving time. So once I am done with this selection, I am going to press apply here, and you see the default element edge size is 14.523 mm, which may be good, holding good to this type of edges, but these are very small edges, so we need to say we'll reduce it to 2 mm or so. And once we have done this, we are going to regenerate the mesh. We are going to regenerate the mesh by right clicking on that, and we can just say generate mesh. Now you see, in comparison with the previous mesh, what happened, the refinement has occurred at this particular edges. And if you can even now go to the information, and you can see that from the statistics you can see the number of nodes as well as elements may have increased. So once I have done this, I need to recalculate all these particular values. So what I need to do is I need to solve the problem once again, because I have changed the total mesh. So changing the total mesh means you are going to change the total skeleton of the problem. So you need to again rerun the calculations, and once you rerun the calculation, now you come to the structural error. See here, so most of the structural error has gone. So this is how you can use the structural error option to refine the mesh in the areas of critical say requirement, and then you are going to have a good mesh without much increase in the computational time or effort. So in the next lecture we are going to see how to analyze an assembly. Until now we have we have analyzed 3D objects, single components, but in the next lecture we are going to go and we are going to analyze a 3D structural problem, assembly problem, where we are going to define contacts, and we are going to see how to change the behavior of the contacts, and we are going to apply these same loads, structural loads, and we are going to see whether this is going to withstand the loads or not. Thank you. Problem, we have an assembly of a Kelvis pin, and you can see in such type of structures here there is a Kelvis attachment. Here in this problem we are going to have a yoke, and we are going to have a U shape, and we are going to have a pin, and all these parts are made up of structural steel. On the other end we have a load of 1 MPa that is applied on this particular face, and this particular face is fixed, and all of these parts are made up of structural steel. What we are going to do is we are going to create the contacts, and we are going to use the no separation contact behavior for all the contacts, and then we are going to study what are the stresses that are occurring in each individual part, and then also we are going to see how to use the contact tool present inside ANSYS Mechanical. Thank you. Pelvis assembly, I am going to just go to the static structure once again. I am going to drag it and place it on the project schematic, and as I've told you, all the parts from this particular pelvis assembly has been prepared by structural steel, so we need not enter any other material in the engineering data. And then I'm going to go to the geometry cell. I'm going to right click on the geometry cell, say import geometry, and I am browsing and I'm going to select pelvis assembly step, and I'm going to open it. And once I have imported the required geometry, I'm going to double click on the mechanical or a model cell from which I'm going to get access to ANSYS Mechanical. I have got access to the ANSYS Mechanical with the pelvis assembly model imported inside it. And remember, there is one additional option known as the contacts when coming to this particular assemblies. So what happens is, see here, if you take this two parts, see this U shape is going to be in contact with a yoke at this particular surface. So wherever there is a contact like this, the automated contact tool inside ANSYS Mechanical is going to generate automated contacts. So here you can get access to this contacts in the connections group. You can just expand the connections group and then you will get a contacts group, and you can see there are three major zones where the contacts have been applied. See here, for example, if I select this contact region, so this contact region is the region where this pin is going to be in contact with the U shape. See here, what happens, this contact body is represented in red in color, which you can identify from here, and the target area is represented in blue in color, which you can identify from this particular figure. So see this from this two figures, you will be able to see what are the target bodies and what are the say contact bodies. So as I've told you, by default this connection or this contact manager inside ANSYS Mechanical is very efficient in creating contacts. You need not create any additional contact. Likewise, you can select this contact region 3. See, if you select the contact region, see this top surface is going to be contact with this surface, as well as this surface will be in contact with this particular surface. So our ANSYS has generated a contact. And remember, the only thing with this contact manager is by default all the contacts that are created will be bonded in nature. So what happens, for example, bonded contact means if you take two pieces and you glue it with some adhesive, then the nature of that bonding, nature of that contact will be a bonded contact. But here, as specified in the problem, we need to have a frictionless contact. So what I am going to do is, I am going to select this contact region, and here in the definition, see here, from the definition, the type of contact is bonded contact. One thing is you can use this automatically generated contacts, or otherwise you can also create contacts manually. For now, what we are going to do is we are going to use the contacts that have been automatically generated. So I'm going to select this particular contact, and then I'm going to say go to the definition. In the definition type from bonded, I'm going to just make it no separation contact. Previously I have told you that it is a frictionless contact. Sorry, it is a no separation contact. We need to change it to no separation contact. And now I'm going to use the same procedure. Go back to contact region, and then go back, change the behavior from bonded to no separation, as well as from the contact region 3 also we can just select this particular frictionless no separation contact. So this is how you can use the automated tools. But now what I am going to do is I want to just show you how you can define contacts manually. So for that purpose, what I am going to do is I'm just going to just delete this third contact. Say I'm going to delete this contact by just right clicking on that, and I'm going to just press delete. Now what happens is we don't have any third contact. We have only two contacts. One contact is pin to yoke, and the one is a pin to U shape. Now what we should be defining is the contact between this U shape as well as this particular yoke. What I'm going to do is as I've deleted the already created contact, I'm going to go and say insert, and then I'm going to select the manual contact region. And now in the manual contact region, I need to select the faces which will be acting as a contact and a target. So what I'm going to do is I'm going to just select this contact group, and I'm going to select this face, and by pressing Ctrl I'm going to select this face. See here. So what happens in the preview, you can see that those two faces have been applied. So I can just select this one by pressing apply. Now I need to specify the target. In order to specify target, one thing you can do is you need to access these top faces. So in order to get access to these top faces, I'm going to just select this particular body. I'm going to go to the body selection. I'm going to select this body, and I'm going to right click and say hide body. And once I hide the body, I will get clear access to this top faces. So I'm going to again go back to the face selection, and in the face selection I'm going to select this face, and by pressing Ctrl I'm going to select this face, and I'm going to apply. And once I apply this, see here I have created a contact. But here by default, as I told you, the behavior of the contact is always bonded. So what I'm going to do is I'm going to change it to no separation contact. So this is how you can use the automated tools inside this particular ANSYS Workbench, or otherwise you can also create contacts manually. So in the next lecture we are going to see how to apply the boundary conditions as well as the loading conditions in order to analyze this particular design. Thank you. How to create automatic contacts as well as manual contacts in the previous lecture. Now what we are going to do is we are going to mesh this particular object, and once we generate the mesh, we are going to apply the loads and boundary conditions. So for that purpose, after creating this contents, I'm going to just right click on the mesh and say generate mesh. And see, once I have generated the mesh, see here this settings, whatever the default settings it has used, it was not able to represent this circular pin accurately. So what happens now, if we are going to go forward and solve this particular problem, we won't be able to get accurate results. For that purpose, what I'm going to do is I'm going to right click on the mesh, say insert, and in the sizing I'm going to say, instead of selecting sizing, I'm going to take the refinement option, and I'm going to select these edges. So in order to select edges, I need to go to this edge selection tool. So I have gone to the edge selection tool. I am going to select this edges, these two edges, as well as say I'm going to select this edge, and or otherwise what I'm going to do is, instead of selecting edges, I will just say select this particular total body. So I'm going to select the total surface. I'm going to select this face as well as this face, and I'm going to apply. And once I select this one, I can give the refinement levels. There are 3 different levels, where 3 is the maximum level of refinement you can ask for. So 1 means it is going to refine a little bit. So I'm going to press 3 and set 3, and I'm going to regenerate the mesh. And once I regenerate the mesh, I will also bring back the yoke. So I'm going to right click, say show all bodies, so that every body is being represented. So I think now it is fine, the mesh is fine. So what I'm going to do is I'm going to go to static structural, say insert, say fixed support from here, and I'm going to select this face as my fixed support, and I press apply. And once I apply that, I can just right click on this one again, and I can just say insert, and I'm going to go to the pressure, and I'm going to apply the pressure of 1 MPa, and the direction is so the direction I require to apply the load is an opposite direction. So what can I do is I can just entering -1 instead of 1, so that the direction is in the required the direction is in required direction. Then coming to this, I need to solve this particular problem. So I will right click on the static structural, and I can just press solve. So once the problem is solved, I can just right click on this to get the say stresses, deformation, and other sorts of options. So I can say directional deformation, as we applied load in the x direction. I want to keep the orientation to x direction itself, and I'm going to say insert. I'm going to go to stresses, equivalent stresses, and I'm going to just evaluate all the results. So this is fine. Okay, so we have applied this particular load, and it is causing deflection in this direction. So if I just animate the result, see the deflection is going in the x direction, and the deflection here should be 0 as we have fixed this particular part. Okay, then fine. So you see, according to this animation, you can say this particular object has failed because there is a lot of deformation. But remember, this is not the actual scale of deformation that you are going to get. It is just for representation purpose only. If you want to change the scale of the result, you can go to the results tab, and in the results tab you can just change. So if you put true scale, see at the true scale, are we able to see any deformation? Very negligibly we are able to see the deformation. So this computer just scales up the deformation so that it can give us a sense of how the deformation is occurring throughout the body. And finally, whatever the result or whatever the decision you are taking, it should be dependent on these values, not based upon these animation values. And you can also even increase the scale of deformation, you can decrease the scale of deformation, you can keep it to true scale, or you can also keep it to undeformed. And then once you go to this, this is known as a geometry. You can see the exterior geometry, see like this, and you can also view the geometry as isosurfaces like this one. So you can see edges, so no edges, and say undeformed wireframe, or say with a deformed undeformed model. And then the option is the show elements, so it is going to show the elements. And there is one good option known as the probe. So if you select the probe and just select a point, at that particular point you are going to get the value of the selected result. So if it is a directional deformation that I have selected and I am watching it, on whatever point I am going to select, I am going to get the deflection value at that particular point. For example, if I change it to equivalent stresses and I just select, go to the probe and just select this particular points, I can see at that particular point this is the value of the stress. Even you can point out where the maximum stresses and minimum stresses are occurring. You can just click on the max and you can click on the minimum, so that you will be able to find this is the particular area where the maximum stresses are occurring, and this is the area where the minimum stresses are occurring. So this is how you can use this results tab. We have finished, we have seen some additional examples from the results visualization tab, and we can also use this vectors and other sorts of things for other problems. Then finally what we are going to do is we are going to use a tool known as a contact tool, and we are going to see what is the status of the contact. So I will right click on the solution, and in the results tab I can go to the tools and I can select the contact tool. And once I select the contact tool, I just need to regenerate the result. So for that purpose I am going to evaluate the solution, and see here what happens in the contact tool. If I put up status, what happens, see here, first of all it is showing me where are the areas it is over constrained or under constrained, where it is sliding, where it is sticking, like this. So what happens is this area is going to slide. This is the type of contact we require. So what happens is it should be sliding to some extent. So this is how you can use the contact tool. So what happens, before the particular loads being applied, the contacts behavior will be something, and once after we have applied the load, what happens to the contact we can see, we can analyze using this contact tool. In the next lecture we are going to see how we can reduce the size of the model by taking the symmetry into account inside ANSYS Workbench. Thank you. Particular problem, we are going to take a flywheel. It is a simple flywheel model, and it is made up of again steel, and it is rotating at a speed of 100 radians per second. The important thing is we need to find out the centrifugal stresses that are developed into this particular body, and then how we can reduce the geometry. We also see the demonstration of the process, how we can reduce the problem size using the symmetric nature that is present inside the geometry. Thank you. To perform simulations on this flywheel, we are going to select the static structural again, and we are going to drag and drop it on the project schematic, and the material is steel, so I need not change the material. I am going to right click on the geometry cell and I am going to import the geometry. So it is nothing but a simple flywheel geometry, and I am going to press open, and then I am going to double click and open the mechanical module or ANSYS mechanical module, and once I have opened this, we are going to perform the analysis using the total body, and once we see the results, then we are going to reduce the size of this particular geometry using symmetric options, and then we are going to again perform the analysis and then try to compare the results coming from both of the analysis. So once I am in the ANSYS mechanical, I can just straight away right click, say insert, and go and give a fixed support to these two faces. I am going to apply, and then I am going to right click, say insert. I am going to insert a inertial load, which is nothing but rotational velocity. So in order to define a rotational velocity, you need to give an axis, and then you need to give a, say, magnitude of rotation. So here, instead of, say, defining this particular inertial load or rotational velocity load in terms of vector, I am going to change it to components. So once I have changed it to components, see here, if I see this global coordinate system, this flywheel can rotate about this y axis. So what I am going to do is I am going to select the y component and enter the value 100 radians per second, and once I have given the value, I need not give any extra value. I am going to go to the solution group, and I am going to insert stresses, and I am going to select the equivalent stresses, or otherwise what I am going to do is I am going to just say, because what I want to study is the centrifugal stresses. What happens if the particular flywheel is rotating like this? The centrifugal stresses will be formed in this radial direction. So for that purpose, what I am going to do is I am going to right click on the solution group, and I am going to insert, say, stresses. In the stresses, I am going to select the normal stresses. So once I selected the normal stresses, I can leave the orientation to x-axis itself, and I can just rename it as a radial stresses. Likewise, you can also select a number of types of stresses. You come to the stress, you can select, say, membrane stress is not available for this 3D analysis, but you can say minimum, you can select from any of these shear stresses. You can also see the intensity of the stresses by just selecting it and placing into the, just bringing it into the solutions group. So once I am satisfied, I am going to right click, say solve. So once I solve the problem, I can get a value of the radial stresses that I have calculated using the total geometry. Now coming to the mesh, just we have used the default mesh, and our statistics show that we have somewhere around 2609 nodes with 1238 elements. So we are going to compare these values with the values that come in the further analysis, that come from the other analysis where we are going to reduce the geometry size. So once we are done with this, I am going to just minimize this one. Now what I am going to do is I am just going to create, say, go for a static structural again, and then once this static structural is loaded onto the project schematic, I am going to right click on the geometry cell, and I am going to open the design modeler, because what we need to do is we need to, say, edit the geometry. So for that purpose, I am opening this design modeler. Once I have opened design modeler, the first thing I need to do is I will go to the units, and I am going to change the units to millimeters, and then here, see, I can just come here, say file, say import external geometry file, and then I can select the particular simple flywheel step file, and I am going to open this particular file. And once I have imported this particular file, I can just right click, say generate, to generate the body. Now I am going to go to the view tab once again, and I am going to change this frozen body transparency. Now what I am going to do is, see here, if you observe clearly, this particular body can be easily divided into 4 pieces by selecting the plane of symmetry. So for example, if I just draw a line here and I draw another line, see here, this particular bodies will be converted into 4, or it will be divided into 4 number of pieces. So for this, what I am going to do is I am going to go to the tools option. In the tools option, there is one thing known as a symmetry. When I select the option of symmetry, it asks for a plane of symmetry. So I need to define a plane of symmetry for this particular object. See, if I just click on XY plane, see here, if I select this particular plane, what happens? The half of this particular geometry will be gone and the half will be remaining. So if you see, with respect to this x-axis, we have symmetry about both sides. So I am going to use this XY plane first to create the symmetry, initial symmetry. So I am going to apply, and then I'm going to generate. See, now what you will do is, you can see half of this particular body has gone. Now what I'm going to do, see, if I'm going to select ZX plane once again, see, about the x-axis we have symmetry for this particular body. So now what I'm going to do is, I'm going to go to the tools, go to this symmetry option, and in the symmetry option I'm going to select the ZX plane. And remember, the geometry which is nearer or which is on the side of the negative axis will be gone, will be deleted. So I'm going to just right click and say generate once again. So if I had generated, right now what happened is, Z axis is pointing upwards, so we were not able to delete this particular geometry. So for that purpose, what I'm going to do is, I'm going to just delete this symmetry once again. So instead of this particular plane, we can select this YZ plane. So now what happens, see, this particular part which is on the negative side of the Z axis will be removed due to the symmetry when I apply the symmetric option. So I'm going to go to the tools, then I'm going to say symmetry, and I'm going to select this YZ plane, and then apply, and I'm going to generate this particular option. See, now we finally got the quarter piece of this particular object. You see, you not only have the option of dividing this particular body into 4 parts, you can also use that particular ability to reduce the number of nodes and elements and computational time for your FE analysis. So once you are done with this, you can just close this particular geometric modeler, and you can just double click on the model, and once you double click on the model, ANSYS Mechanical will open. So the only thing you need to do is, when you take up the model, you should think, is there any axis about which I can have this particular symmetry? And once you found out that, then you need to take the symmetry option, and then you can cut this particular body. Then in reducing this particular body, the main rule is the Z axis should be lying in the plane perpendicular to the symmetry plane. In order to explain clearly, I will go back to the design modeler once again, and I am going to edit the geometry once again, and I am going to clearly, once more I am going to clearly teach you the concept of symmetry. So I am going to just delete this symmetry, and I am going to delete this symmetry as well. So okay, now you have a total body. Now I am going to select one plane. So if I select this particular plane, see, there is a symmetry in the body about this x-axis, or there is a symmetry for this body about this particular z-axis. Okay, that's fine. So we now found that about this particular axis we have symmetry in this particular body. Now, so if I want to reduce the body using the symmetric tool, the main rule is, this particular z direction should be lying in the plane which is perpendicular to this symmetric plane. So this is a symmetric plane, and this is the z direction. So now what I am going to do is, see, I am going to go to the tools, select the symmetry, and once I select the symmetry, I can apply this plane, select this plane and say apply, and now see, this particular half will be deleted because this particular half is on the negative side of this particular z axis. So I am going to right click, say generate. Once I generate, see, as I have told you, this particular half has gone. Now you can just add symmetry, say go to tools, add symmetry, and now if I select, say, see, if I select ZX plane, here also there is symmetry about x axis in this particular plane, but what happens is, this particular z axis is not perpendicular to the plane of symmetry. So if we take the plane of symmetry will be somewhat like this, and this particular z direction is aligning with the plane of symmetry. So if the z axis is aligning with the plane of symmetry, you won't be able to cut or remove the material. See, for example, if I select this one and press apply and say generate, see, I won't be able to delete any material. Did I delete any material? Yes, I have deleted the material, but that was the material on the bottom side which was in the negative direction of the z axis. Then, so I am going to add another symmetry. Go to tools, go to symmetry, and then I'm going to select this particular plane and say apply, and I'm going to just say generate. Once I generate, I'm going to get the final symmetric model. So once I have satisfied with this final symmetric model, what I'm going to do is I'm going to just close the design modeler, and in the next lecture we are going to see how we can apply the loads to this and solve the problem, and we are going to compare it with the previous full body model results. Thank you. We are going to apply the boundary conditions, and we are going to solve this symmetric model by just double clicking on the model cell. We are trying to open the ANSYS mechanical. Now what happens is, it is asking upstream data has been changed, would you like to update? So what happened is, I have changed the geometry, and now the model ANSYS mechanical module is asking me that you have changed the model, so would you like to update the model? Yes, I would like to update the model. And then coming to this, I am going to right click, say insert, I'm going to right click on the static structural, say insert, and I'm going to select the fixed support, and I'm going to fix this particular face and say apply, and then I'm going to right click, say insert, and I'm going to insert this particular rotational velocity, and I'm going to change it to from vector to components, and I'm going to give 100 radians in the 100 radians per second velocity, and I'm going to right click, say insert, say go to stresses, equivalent stresses, and I'm going to just right click, say insert, I'm going to go to the stresses. In the stresses, I'm going to go to the normal stresses, and I'm going to leave this in the x-axis. See here, here also, if we take the global axis, this particular x-axis is going to align with the radial direction of this flywheel. I'm just going to rename it as radial stress. Then I'm just going to right click and say solve, and once I solve, I will get some values, and from those values I can compare these values with the previous one. So first of all, I will go to the mesh, and I go to the statistics, and see here the number of nodes were 1600 and the elements were 749, whereas in the previous case the number of nodes were 2609, the elements were 1238. So what happens is, in the previous case it had to solve 2609 into 3 number of equations, but now in this case it should be only solving somewhere around 1600 into 3 number of equations. So you have seen the number of equations to be solved by the computer has decreased, and this particular thing, if it is in a case of a very complicated problem, it will save you a ton of resources, ton of money, ton of time for the analysis projects. So okay, coming to the results, see here. So I'm going to get a result somewhere around like 2.153 MPa in the radial direction. So I'm going to just switch back to full model, and I'm going to see the radial stresses. See here, I'm going to get 1.98. There is a little bit difference. So this little bit difference can be avoided by performing a convergence study, by changing the different mesh settings, and you can just remove this particular ambiguity that is present between these two models. So this is how you can just use the symmetry option present in the geometry to create a model with less number of nodes and elements, and perform an static structural analysis or other type of analysis very effectively. In the next section, you are going to perform analysis on 2D objects using ANSYS Workbench. Here we are going to simplify the 3D objects as 2D objects, and we are going to learn how to perform analysis on them inside ANSYS Workbench. Thank you.